going to proceed with the next talk, and we're very excited to have Philipp and Philipp Reißel here with us to talk about approaches beyond BERT and the training of German language models. As a short introduction to our speakers, Philipp is the Guild Lead Artificial Intelligence and Data Analytics at T-Systems, and Philipp Reißel is the founder of a company called ambeRoad that offers NLP and AI services specifically in search engines, as I've understood. So now the two of them will present you a talk and give you a deep dive into how they've trained one of the, if not the best performing, currently open sourced language models for German. And they'll also be introducing Electra, which is a relatively novel approach to pre-training language models that uses discrimination rather than token masking and is a lot more efficient than masked language models are. So very excited to hear from you two.
Yeah, welcome to our talk about German language models and training and evaluation.
So we were already introduced by you. Thanks for that. A few words to myself. Yeah, I'm Philipp. I'm one of the founders of ambeRoad. We are creating the Google search engine for your company internal data, based in Aachen, and always looking for people who want to join us and are experienced with NLP and programming at general.
Yeah, I'm Philipp, data scientist at T-Systems. I'm not only working on NLP stuff, but also on time series prediction. Basically predict anything, use cases with flat data, for example, and anomaly detection things.
Okay, yeah, then let's look at how we came together. It all started back in June, when Philipp was looking for some German data base from which he can train a Roberta model. I was also looking for some German databases to train a new German model as well, because the current ones which were available back then had some limitations, and I thought it could go better, and Philipp thought that as well. And then we came together, and 10 weeks after that, we released the first version of our German Electra model, which we updated later, and was by its release the best German model, at the efficient German model, which you can use for multiple tasks, all kind of classification, etc.
Okay, so now I want to give an overview of how to train and use language models. First, there is the model language training, where you need a text corpus, in our case, a German text corpus, and then you do the language model training, which is being done without labels, just the text, and this is called self-supervised learning. And the result of this is the language model, which is, at the end of the day, a special neural network, which did build a general understanding of the language and its structure. And after that, you can use this language model to train on your so-called downstream task, which is, for example, to detect, let's say, a sentiment in Twitter data. Let's say people are talking about your company and having positive, negative, or neutral sentiment, and you want to detect it. So you need the text and labels, and then you take the language model and apply a so-called prediction head on top of it. And this is called transfer learning, where you take one neural network or machine learning model and train it on a different task. And then you apply supervised training to train your final model for production. And as an optional intermediate step, you could do something called domain adaptation, which adapts your general purpose language model to a specific domain. For example, we have one listener who said he is working on engineering NLP tasks. So you could take in your engineering texts, the engineers writing emails about their daily problems and so on, and train and adapt your general purpose language model to this specific engineering domain, which is basically done the same way as language model training, but with a specific domain.
So which problems occur in practice when trying to apply these pipelines to your model training? At first, there's always an, like it's in most machine learning problems, the task to get some data. As we heard in the first talk, you can get label data for some money, or if you have not so much money and need there are the base option is Wikipedia. What some other German language models used as well was open legal data, which is laws and court rulings. Or other options are as well the Oscar corpus, which was just recently released, which has as a smile in the trash can, or the library Genesis, which we didn't use because of legal reasons, because it's like the Pirate Bay for books. So it's, yeah, in practical usage, it's pretty hard to use that kind of databases. One other main challenge is the specifics of in German, you have the word, the noun compounds, which is you simply append nouns together, some single characters in between, and this makes it for some splitters really hard to get meaningful of that. So you see down below, BERT tokenizer would tokenize that, and it's nowhere near the human approach how to separate these words. Last challenge is, of course, where to compute and store all the intermediate results and final results, this processing, the downloading, the multiple training runs to adapt your parameters, and finally the publication of your results.
Okay, so what are the ingredients or the steps to train a language model? The first step is that you have to get a text corpus, and this text corpus has to be pre-processed. It has to have one sentence per line, which is not an easy task, because yeah, you have to split your text into sentences. And Philipp, when you can push your right arrow, yeah, we evaluated different libraries to do this sentence splitting, and found out that for our needs, Zomayo performed best. We compared it to Spacy, for example, but for English and German language, this Zomayo tool is the best. So when you have split your corpus into sentences, you also have to place one blank line between documents, and your corpus should be large. Philipp will go into detail later, and you have to cover your whole language domain. The vocabulary is the second step you need. That is basically built from your text corpus, and it contains all the tokens and special tokens your model can process. I will show examples how these tokens look like later. Then you have to come up with a tokenizer config. It's how the sentences are split into tokens. For example, there are settings about the casing, if it should be lower casing or upper casing, if the accents and umlauts should be kept or dropped, and how long a sentence can be on maximum. The fourth step is to configure the model and the model architecture. For example, you have to specify the number of your attention heads, the embedding size, number of hidden layers, and so on. And the last step is that you have to configure the actual training. For example, your batch size, your learning rate, and your train steps.
So let's dive a little bit the fourth point, which is the model which we used. Of course, we didn't build a new model from scratch, but we relied on already built structures from other researchers. So as a basis to all, basically it's BERT. So released end of 2018 by some Google researchers. It became quickly the basis for nearly everything in natural language processing classification. Not used for that. But how is the BERT model trained with the unlabeled text? Basically, it has two main objectives that are given to BERT during training. The first one is the whole word masking, which means there are given sentences into BERT, then one word is masked out, and BERT predicts and tries to predict the missing word, basically a fill-in-the-blank task. The other object sentences which are put together, and BERT tries to predict if these sentences are coherent, so if there are after another in the original text or if they are randomly put together by the algorithm. And through these two tasks, BERT learns some general natural language understanding and thus can be applied to lots of other tasks. One new approach is Electra, which is also from Google and Stanford researchers, which incorporates a bit like a gun-like structure. Guns originally used in image processing and generation. They consist of two models. You have a generator and the generator tries to fool the discriminator. So you pass a sentence through the generator, then the generator tries to replace tokens, not mask them as in BERT, and then the discriminator tries to detect which tokens are original and which ones are replaced. The advantage here is that the discriminator tries to look at every token and not only as BERT as at the mask tokens. In more mathematical terms, the discriminator can build the gradients for every word, not only the mask word, which speeds up training and makes it more efficient. Over the training time, both the generator and the discriminator gets better. This means the generator learns as well that he should change out words which are pretty similar. The discriminator gets better in the way that it can detect over time very small changes in the sentence sentiment and tries to detect that. One disadvantage here is that you have no next sentence prediction task. It's pretty hard to create a generator for the next sentence prediction because the generator and the discriminator together have to be derivatable. So you can't simply use some random choice algorithm. And one third approach, which you saw at one of the first slides, which was originally in Philipp's mind, was to train a Roberta, which is from the code very similar to BERT, so nearly no changes except that the next sentence prediction is dropped as well, because the authors found out that at least on the benchmarks, the next sentence prediction doesn't lead to a better performance. What they did change in Roberta is they trained with a far larger batch size, and far more data. Based on Roberta, so same architecture is XLM Roberta, which is the multilingual Roberta, which is simply same architecture, but a multilingual vocab file and multilingual data as well.
Okay, so let's talk about the tokenizer. So we have this language model, which is a specialized neural network. And somehow we have to push the text through this network, right? But the neural network cannot work with text. It can only understand numbers and tensors. And so the first step is to split your text. And this here at number 1 is an example of a tokenizer, a so-called word piece tokenizer that splits this text into tokens. And yeah, you can see that the text is basically split on white space, but the tokenizer also sees the dot at the end of the sentence and splits it to its own token, and it splits longer words like kündigen into multiple tokens. And these tokens are then converted to integers by using the vocabulary, where you have one token per line, and basically it maps the token to the line number, which is the integer number for this token. And then at the beginning, at the first layer of the sentence of the language model, you have a so-called embedding layer, which converts these integer numbers into vectors. So the first thing we notice here in this sentence is that the first word, ich, is written with uppercase at the beginning of the sentence. But this word might also appear in the middle of the sentence, and then it is written a lowercase. So there are two different versions of the same word, but they have the same semantics. So our thought about this is that the model has to learn that it often sees two different versions of two different tokens, but has to learn that they are semantically the same. So this puts a burden on this model, and we don't want to have this burden. So we chose to use a lowercase tokenizer, which is seen in the middle. Number 2 is a lowercase tokenizer. Yeah, and you see that it converts the text to lowercase. But also you can see that it drops the umlauts, right? It changes the meaning of the sentence, because ich möchte meinen Vertrag kündigen. I want to quit my contract has a different semantic and a different meaning of ich mochte meinen Vertrag kündigen, which means I wanted to quit my contract, right? At the first example, a company maybe could still do something to change the customer's mind and avoid this quitting. And number 2, it's already too late. It already happened in the past. So there is a semantic in the umlauts. and we wanted to keep those umlauts. So we noticed that the transformer library is always dropping umlauts when it is configured to do lowercase. So we had to come up with a pull request for a transformers library and also for the Electra library, and introduced the strip accents parameter seen at step number 3. So there you see that the text is converted to lowercase, but the umlauts are not dropped. And in my opinion, a second advantage of lowercase is that when you process casual text like Twitter messages, the people often do not care about casing and write everything in lowercase. So our model is, it's easier for our model to process this kind of data.
So now, after we have defined the tokenizer and the model architecture, let's see what we did with the data. So I've put up here the two extremas. First, the lower base is the complete German Wikipedia, which was used in models before, which has a size of about 6 gigabytes and around 2.5 million articles in it, free for everyone to download and easy accessible. You have to watch here because the y-axis is logarithmic scale. So the other extrema, the largest database which you can possibly think of is the Google index, which is estimated at about 100 petabyte and 50 billion web pages. Of course, Google isn't happy about giving that out, so we had to come up with another solution. One pretty well-known source for that is ComCrawl, which is a foundation, and once per month they crawl the internet. That means they don't take a complete snapshot, but a very large snapshot of about 300 terabyte and offer that free for everyone to download. The monthly snapshots go back in time about 6 years in a high quality, about 10 years with low quality at the beginning. And good for us, ComCrawl also extracts the text only. That means they remove JavaScript boilerplate, HTML boilerplate and commands, and directly provides that as well. That is then about 10 terabytes per month, which is downloadable. The guys from XLM Roberta use that approach as well, and they offer a very nice tool on GitHub, which is called CCNet, to do the additional pre-processing afterwards. It has very high constraints of resources. So every month of processing is about 20,000 CPU hours, and you need approximately 30 gigabyte of RAM per CPU core for that. Then what it's coming out is first, you remove duplicates page, which filters out cookie acceptance banner, data policies, which are not always often they are English. So when you filter out the boilerplate, you then make detection, and we focus only on German data here, also because of constraints for storage. And after having all German web pages extracted from these monthly snapshots, which was approximately 1.8 terabyte of raw text data and about 1 billion web pages, then we do an additional step, which is filter for high quality. So the internet has lots of bad sites, lots of low quality colloquial talk, which we don't want to include, or clickbaiting websites, which we also don't want to have. And data set. By now, it has grown over time to 400 gigabytes and 140 million web pages, which are offering on request. We are also looking for someone who want to hold network. Traffic is a bit too expensive to make it free for everyone because of people who want to abuse that. But everyone who needs it gets it. At the time of our version 1 of our model, the database which we used was one monthly snapshot, which was 50 gigabytes of raw German. Then last step before the training is who's gonna pay for the computational resources and how can we maximize our impact? So how can we get the best out of what we have? I've very rough performance comparison between some GPUs, and down below the price for spot instances at Google Cloud approximation. You see the largest single worker you can get at the moment is 16 A100 GPUs. Everything above that threshold gets a little bit messy for implementation. So you have to care about how far are the servers, how good is the internet connection between them, are they in the same area, how do you make sure that the accumulation of the weights is performed fast, and that's always a bit hard. We don't want to do that at this time, especially because we had a certain time window where we want to finish. So we switched to TPUs, which are sadly proprietary to Google, so they control the whole ecosystem, but they also them for free. So in Kaggle, you get a TPU v3 which is basically equivalent to 8 v100 GPUs, and you can use it, I think, 50 hours per week for free. Also at Colab, you can use some older TPUs, and you see on the scaling, they are between a factor of 2 and a factor of 5 more efficient when it comes to price per performance than even the latest NVIDIA GPUs at these cloud hyperscalers. Most importantly, you can scale up these TPUs pretty. You see one TPU here at the right bottom, and you can train them as they are one worker, even though they are somehow connected. But for you as an user, they behave like one worker. Even when you scale it, you see here the scaling to 64 cores. You can scale that up to 2000 cores, which makes it pretty easy to get really large models trained and into production fast. One short approximation here with approximately 1000 GPU hours from a V100, and we for the one model we trained, we took approximately twice that much. We had additional runs as well, so we used maybe 5 to 6 times, so 5 to 6,000 GPU hours in total for that. So now everything is set up, and let's see what the result was. So these are training results. You see, we've done some experiments, tuned some hyperparameters. At the end, we came up with hyperparameters, in most cases, the defaults, which we found out were the best. We experimented also with vocab sizes, where we then agreed to staying at about 32,000 vocab size at the end. One important thing to see here is our original publication was the version 1, which we stopped at 700,000 points. We later extended that to 1.5 million steps, and you may see the increase in loss right after the V1 spot was stopped. And that is one point where you have to be very careful, because these natural language models train with a linear learning rate decay. That means you set up a learning rate, and that is 100% at step 0 and decreases to 0 at the end. As we originally wanted to train only the V1, the learning rate went the end of V1. When we then resumed the training to get the V2 as well, the learning rate was readapted to make the linear decay to the new 1.5 million steps. That means that the learning rate suddenly jumps up again, and the model goes out of local bad. If it's stuck in a local extrema, it's probably good when it gets out. When it's already in maybe the best local extrema or global extrema and it jumps out of that, it's probably bad. There's no easy way to know that, but as a little spoiler, the V2 beats in every benchmarks the V1. So yeah, you definitely should use the V2, sorry. And then I will hand over to Philipp once more.
Yeah, so we did an evaluation to compare language models, not only our own. Philipp, I have a small echo. Perhaps you can mute. Yeah, so we did an evaluation, not only for our own models, but for all German language models. We did this to evaluate language models. You have to train them on a downstream task. So we used the German eval 18 task. It is an open data set with offensive language. And we used F1 macro score to compare the performance. We did an individual hyperparameter optimization for every single model we analyzed. And yeah, we did use the automated hyperparameter optimization tool Optuna to do this. And to avoid the situation where we have hyperparameters that prefer one model and penalizes the other model. So we have a fair game to compare the models. And we applied cross-validation to avoid overfitting on the validation set. We did, when we found the best hyperparameters for every single model we compared, we did multiple evaluations. So we randomly initialized the networks over and over again with the same parameter set, trained them, and then checked the F1 macro score and logged them. And those scores are compared with box plots. So on the next slide, you see that in this evaluation, we saw that, can you go back? Yeah, we saw that some models are suffering from undertraining, so they just did not see enough training data, while others benefit from an extensive training. So Philipp came up with a brilliant idea to further train it. He already described it. So when you show the blue arrow, we moved from the 766,000 steps that were suggested by the Electra paper to 1.5 million steps by further training it with the same settings, with the same corpus, but just doubled the training steps. And on the next slide, you can see our results. Yeah, these are all relevant German language models at the moment. So the three models on the left side are the old models. The left is the first German language model trained by DeepSet AI. And then the two DBMDZ models trained by Stefan from the Bavarian State Library and open sourced. Then we have 4 models called G-Electra and G-BERT in the base version and the large version. And these models are also trained by DeepSet AI and Stefan from the Bavarian State Library and open source. They wrote a paper about it, and they are evaluated here. Then you see our base models, Electra base models called G&G Electra. That stands for German NLP group, and then the Electra model. And you see the version 1 and the version 2 here. So when you compare G&G Electra version 2 with G-BERT base, you can see that the median of both box plots are outside of the other box. So statisticians would say that it is likely that there is a statistical significance. Yeah, and at the right side you see the two large models which have the best performance as expected. And two things are important to note here is that basically the large Electra model should perform better than the large BERT model, but the guys doing the training did a little mistake. You can read it in their paper. They used a batch size of 1024 to train the large Electra model, while the Electra model suggests a batch size of 2048. So this model only saw half the training data as it is supposed to see. And another nice thing to see here is that these the second and the third model are from the same structure and trained with the same parameters, but the only difference is the casing, and the uncased model performs a little bit better, which underlines our hypothesis that casing puts a burden on the model, and it is a good idea to remove it. Yeah, that's our evaluation here.
So we now wanted to go over into the discussion because the German language model was pretty fun, but we are not quite sure if that's the right path to go in the future. So basically what we have done, and there are some papers who are doing this much more intense than we did, training some monolingual model, saying, we are the best in the language. But there are also very large multilingual models from companies like Google or Facebook. And you see when you compare the computation time that they invest, it's orders of magnitude higher than what everyone else can invest in these models. And what we want to find out in the future is, of course, can't you just adapt multilingual models and beat everything that is monolingual? Because maybe you know that from a practical point of view, when you're looking for very specific informations, you often switch to the English Wikipedia because there's no knowledge of that in German language. So why don't we do that with the multilingual models as well, transferring cross-lingual knowledge from one language to another? This regional knowledge and adaptation of country specifics, which you somehow have to get then into these multilingual models. And that's exactly where we wanted to start some little discussions with you, to get in touch with you guys and see what's your idea, think about future approaches, and what's the right path to go.
I really thank you all for listening. And I mean, if there aren't any further questions here, we would like to suggest to start the discussion in our Slack, or if you don't want to join the Slack, in the forums and the comments of our Meetup section.
Thank you all for joining. I'm also very happy you've all stuck around. You've all participated in the discussion, and thank you very much to our presenters tonight for those fascinating talks. I think, yeah, we've all had a long day, and I look forward to seeing you again on Slack and maybe interacting with you and talking about, I don't know, character embedding based models on that. So join up. And until then, just thank you very much. It's been a pleasure listening to you and interacting with you.